Welcome to energy levels and photon emission. We're going to start off by studying hydrogen. Hydrogen has been studied a lot in the past. Its emission spectra and absorption spectra are very, very well known. So first of all, we have a model of our hydrogen atom here. We've got the nucleus in the centre, and then we've got the various shells that the electrons can orbit around. The electrons, by default, are at the ground energy level. If they absorb energy, they can jump up to higher energy levels. If, by the way, you are studying A-level chemistry, when I say energy levels, I'm talking about orbitals. So the electron at the ground state can absorb energy and jump up to higher energy levels. There are lots of ways that these orbitals, these energy levels, can be represented. Here is a model of the atom in the way that you're probably most familiar with it, particularly at GCSE, where you've got the nucleus in the centre and then you've got these circular energy levels around the nucleus. More commonly, we represent the energy levels and electrons on diagrams like this that look like a ladder with uneven steps. And this diagram comes from a short section of this diagram up here. Okay, so you can see that this now looks like a ladder. Sometimes the energy levels start with the ground state being 0 and working our way increasingly positively until we get to the ionization energy, which is the n is equal to infinity level, with ground level being n equals 1. This is a very common way of representing it, where we can see the ionization energy up here. But you need to be familiar with another way of representing it as well, where the ground energy level is a negative number and the ionization energy is 0. It's as though the electrons are trapped in a well, an energy well, like a hole, and they're trying to climb their way out to freedom. You can be presented with either and be asked to calculate the frequencies or the wavelengths of photons that are given out when an electron falls. It might fall straight to ground, or it might go through several steps. Or you might be asked to calculate the energy of a photon that would raise an electron to a higher energy level, like that. If you're dealing with a situation where you've got positive numbers, or you're dealing with a situation with negative numbers, you're just looking at the difference between the energy levels. I mentioned before that hydrogen has been studied quite a lot, and in fact there are naming systems for some of the more common energy drops and energy increases, and these are illustrated up here. You don't need to know these names, but it might be helpful for context, particularly if you're reading a more advanced book in order to prepare for your exams. If you come across these terms here, then that's what we're talking about. Each one is named for where they're dropping down or being raised up from. Okay. So let's have a look at a couple of examples. We're going to have a look at some examples from the Balmer series, because that gives out or absorbs light in the visible range. And here we have an emission spectra for hydrogen within the Balmer series. So for example, a purple light, a purple photon, is given out when the electron falls from level 6 to level 2. So we would be going from level 6, so 13.2 electron volts, going down to level 2, which is 10.2 electron volts. So we find the difference by taking the largest number away from the smallest number. And then we can convert that energy into a wavelength or a frequency using the equation E equals hf. So we've got 3 electron volts, and that means that we've got 3 multiples of 1 electron volt. And we remember that 1 electron volt is the same as 1.6 times 10 to the minus 19 joules. So we've got 3 multiples of that. So we need to use the SI unit for energy in this calculation, otherwise it won't give us the correct answer. We can't just plug in 3 into this calculation, it'll give us an error. So we have 3 electron volts, and each electron volt is 1.6 times 10 to the minus 19 joules, divided by Planck's constant. We could convert that to a wavelength, remembering, of course, that wavelength is connected by this equation to frequency. Speed of light divided by the frequency that we've just calculated. Please note that I am writing down the rounded value. I've rounded it to 2 significant figures, and I'm going to use the number that's still in my calculator to calculate the answer, and then I'm going to write my final answer out to 2 significant figures. Which is this one over here. So I've just confirmed the answer. 6 to 2, 6 to 2, and that gives out 410 nanometers, which is in the purple range. Now I can do the same for all of the others, and I can do the same for the Paschen series and the Lyman series, and it's the same technique essentially. Okay, let's have a look at emission and absorption spectra. We know that if we have a series of energy levels, that an electron at the ground state can be raised to another energy level if it absorbs this amount of energy. It has to be that exact amount of energy in order to make that jump. If it's through collision with an electron, then this amount of energy will be taken from that electron, and the electron will be left with whatever else is spare. But if it's by the absorption of a photon, then that photon needs to have this amount of energy, and therefore would need to have that frequency. When an atomic electron absorbs a photon, it is absorbed in its entirety, which is different from when we have collisions with external electrons. When an electron falls from a high position to a low position, it emits a photon of that energy, and therefore that frequency and that colour. It may be that the electron falls down in steps, and if it does, then it gives out an electron for each step that it falls through, and therefore the photons given out would have different frequencies. We have something called emission spectra and absorption spectra. An emission spectra is what you get when you have a hot gas and the electrons inside the gas are being excited to higher energy levels by that heat, and then the electrons are falling down and releasing photons. The light being emitted from that hot gas, if we pass it through a diffraction grating, which will allow us to see the spectrum, we get a spectrum that is incomplete. There are lots of gaps, but where we do get light, that is the energy of the photons that are being given out when the electrons are falling from an excited state back towards ground. So we can spread that light out, and this is an emission spectra, the word emission meaning to give out, to emit. An absorption spectra is the opposite. This is where you have those photons missing from the light. And the way it's generated is that you have a light source, and that light source passes its light through a cold gas. And this cold gas absorbs the energy. So what's happening inside the cold gas is that the electrons are being excited to higher energy levels by that incoming light. They are absorbing those particular photons, so those photons with those particular energy levels are being absorbed by the electrons, and then eventually, when those electrons fall back down again, those photons are being given out in all directions. So we have this light coming towards the cold gas. Any unabsorbed photons carry on straight through. The ones that are absorbed are then given back out in every direction. So any that do continue in the same direction as the original light source are going to be much, much, much weaker, especially over the large distances that we're talking about. And so when we finally split the light into its spectrum and look at the spectrum like this, we see dark areas where there are far, far fewer photons being received at those wavelengths. So we see these dark lines and we know, these are the photons that are being absorbed by that particular material. And because every element has a unique set of energy levels, we are able to look at the patterns and see, oh, this must be hydrogen, or this must be helium, or there must be mercury in there somewhere. And we can see what the composition of that gas is. We can do the same thing with a hot gas. We look at the pattern of the emission spectrum, and we can see, oh, well, that's a hydrogen wavelength, and that's a helium wavelength. Oh, look, and there's mercury over there. We can look at the pattern and deduce what the gas is made from. And we use this particularly when we're looking at the atmospheres of exoplanets to check for atmosphere compositions that could support life, for example. A very old application of this is in blacksmithing. Here you can see the emission spectrum for iron. When iron is at quite a cool temperature, it gives off low energy photons in the red range. If you increase the temperature, it will give out these red photons, but it will also give out some of these orangey photons. And the hotter it gets, the more energetic the electrons are able to become, the more excited they get. And when they fall down, they're able to give out higher and higher energy photons when they fall back down again. And what that does is it affects the colour of the metal. So a long time ago, where we didn't have the technology to be able to detect the temperature of something from a distance, blacksmiths relied on the colour of the heated metal in order to figure out if it was at the correct temperature to be able to be worked. And the hotter iron got, the more and more of these green and eventually blue colours combined with the oranges and the reds to produce something that was quite close to white light. So cool iron is red, warm iron is orange, hot iron is yellow, and extremely hot iron is white. So that's where we get the phrase something being white hot. And here is a diagram that is useful for modern blacksmiths to help them to understand what colours they're looking for if something is in the temperature range. The temperatures are over here, the temperature range where it can be forged, where it can be worked like this. So that's an old application of emission and absorption spectra.